Okay, let's give this a go. I have my new setup, new large external monitor, and I'm curious to see how this works. So we're going to be working on a bit more specialist math for Year 11, and we'll continue with vectors, and we're going to be looking at parallelism. So here's some three key points we're going to be looking at. Vectors A and B are parallel if B is equal to Ka. Result of that would also mean that the length of B is equal to the length of A times the modulus of K. K can be positive or negative, and both mean parallel. So you get vectors pointing in opposite directions, and they're both parallel. Although there is a term called anti-parallel, which describes vectors in opposite directions. This still counts as parallel, though. So if K is less than 0, some textbooks call that anti-parallel. Okay. Another key term that we need to know is the unit vector. We went through the unit vectors in x and y direction, being I and j respectively. There are also unit vectors for any vector you can draw. All you have to do is take the vector, divide it by its own length. It will still go in the same direction, assuming that, but it will have a length of 1. You can also do this. You can also make it go in the other direction as well. I've seen the notes that that's also acceptable. I might just work on the focus here. That's a bit more crisp. Okay. The other point we're going to cover in this video is collinear vectors. So if you have vectors which are collinear, they co-linear. Co means in the same, linear, straight line. They will follow a straight line. So you can draw vectors. Those vectors can be off anywhere in space. However, if they're collinear, they have to be not only parallel, but they have to be such a point that they are on the same line. And what that means is they'll have the parallel relationship that B equals Ka, vector B equals Ka, and also they must share a common coordinate point. All right, so we'll go through each of these. I'll go through the examples and we'll look at some further problem solving as we go through. So give myself a bit of space and let's have a look. All right, so this is on page 83 of your textbook, the Hasey book. All right, now that's the same as what I just went through, but the idea, you can see A and B point in the same direction, but they just decided to represent it as A equals KB rather than B equals Ka. Doesn't really matter. It just means if you actually did it the other way, you still have a constant. You'll still be scalar multiplication, but it'll be 1 on K as compared to the other one. So if you had two vectors and you knew they were parallel, you could sort that out. So if, I don't think we need to go through how to do that because it's right here. The idea that if A is parallel to B, then A must equal KB or B equals Ka. Either way will do. If you did it the other way, you get a different value for K, but you still get the same value for S as you work it out. So as you multiply K in there, so that'd be K times S and K times 2. 2 times Ks and minus 1 times 2K from the equation. K equals 1/2 because 2K minus 1 divided by 2, K equals minus 1. Substitute that into the other equation. 2 equals minus 1/2 S times both sides by minus 2, S equals minus 4. And then you've got the other coordinate for B. So that's actually a pair of vectors which are anti-parallel. All right. So unit vectors. We already learned how you can find the length of a vector by taking the modulus. We'll go through that operation again, no doubt. And actually two acceptable vectors are for unit length. If you want to find, if B is the unit length vector of A, and then B equals, and this is actually in terms of any length. You can say any length K can be represented by B times K. So if you wanted a vector of A that had 4 units, K would be 4. You divide out the length of A, so then thereby A divided by modulus A is has a length of 1. Times by 4, B would be 4 units in the direction of A. You can also make it go in the opposite direction by doing this, by doing minus in that case. All right, so let's have a look at that. So example this, if A equals 3i minus j. Find a unit vector in the direction of A. Okay, let's start with that. So A, I prefer to write it. So this is okay. So I'm going to use their format. So I'm going to use 3 and minus 1. Okay, there we go. All right. Start off by let's find out what the length of A is. Well, you have minus 3 squared plus, whoopsies. Well, it doesn't really matter, but let's correct the mistake anyway. It's actually minus 1. Okay, so that has the square root of 10. All right, so the unit, unit vector of A is, okay, would be 1 on root 10 times A, or you can put that on top if you prefer. And thereby, if I actually multiply that in, I could write this as such. 3 over the square root of 10 and minus 1 over the square root of 10. It goes in the same direction, but now this will have a unit of 1. Just for the sake of it, I'm going to prove it. All right, so if I took the modulus of this, root 10 and minus 1 on root 10, what would that do? Okay, you square 3 over root 10 and add it to the square of minus 1 over root 10. What would that do? Well, let's have a look. All right, so 3 squared is 9. So 9 on 10 plus 1 on 10 equals 10 on 10. And that's 1. The square root of 1 is still 1. So you can see, oopsie, that's a bit messy. All right, there we go. Yeah, so we can see that we're still getting, a unit length. It's in the same direction because it's parallel, because all we did was times by a scale factor. But it has a length of 1. So now it's a unit vector of A. That's what we got. B, a unit vector for length and direction of A. Okay, so if it's in the direction, then it has to be the positive. Okay, so let's do that. B, sorry. No, you can't see. Let me adjust the camera. All right, so B is equal to, all right, so 4 units in the direction of A. So say let B equal 4 times A on mod A. Well, that's essentially 4 times what I just did in part A here, which would be, so basically timesing 4 into this would be 12 on root 10 and minus 4 on root 10. Okay. Vectors of length 4 units which are parallel to A. Well, all vectors, okay, well, that would include, I'll call this one C, basically plus or minus A on root A. Now, they use this I and J format. I'm still using the parentheses here, and I'll show you a little trick. I can still keep it like this. I think this is legitimate. I don't like necessarily the I and J. Okay, this still has to be 4 units, so I apologize. All right, so it's still 12, but I'm going to say that's plus or minus 12 on root 10. And the other one, now, if you've already got a minus there and you incorporate a minus or plus, if one's plus or minus and they have to change signs, so one of these, if it's actually going to be in line, like either parallel or anti-parallel, then one must be negative, one must be positive. Like if it's negative then positive, then that's in the opposite direction of the positive and negative. The other one must be minus or plus. So you see it's upside down? Well, that means if this is positive, this is negative. And if this is positive, then this is negative. So yeah, so that maintains that behavior. And you can drop the negative then, because it's incorporating the fact that we flip this upside down. So yeah, these are negatives of each other in terms of yeah, the signs. They are obviously, this one's larger magnitude, regardless. But that's actually all the vectors in that respect. So actually, yeah. And theirs is also an acceptable way of approaching it, but I think I did mine more concisely. All right, so, okay, so maybe I'll have a look at some of these questions. Try some of these yourself. I think question 1 is easy enough. What can be deduced from the following? Well, for like question 2, let's find where let's go up here. Get the camera back up. All right, so it's a bit bright. There we go. All right. So question 2, maybe pick B. RS is parallel. Anti, now that's not a term they use, but I do. Anti-parallel. And has half the length. Of KL. All right. Okay. Find the unit vector in the direction of. I think that's easy enough. We've done an example of that. Right, then the vector. Yep, we've done those. Okay. I might do question 6. All right. Find AB. Okay. B is 4 units from A in the direction. Okay. So in the direction, I've got to make sure now that is not, just by looking at it, the unit direction, because that has a unit of root, that has a length of root 2. I want 4 units in that direction. So basically, if I say, all right, so the vector AB is 4 times by 1 on, oopsie, 4 times 1 minus 1 times by 1 over the length of that, which would be squared, minus 1 squared. I can all do this separately if you like, but I'm just doing it in one hit. So now that is 1 over root 2. So it's 4, if I brought that over here, 4 on root 2 times 1 minus 1. So 4 units, this divides this division of root 2 turns this into a unit vector. So then it's 4 units. So, and also just for a bit of, okay, so I can represent 4 as 2 times root 2 times root 2. I'm going to get rid of that root 2, cancel, and then I can actually simplify this. All right, so then I could say that that vector is now 2 root 2 minus 2 root 2. There we go. That's 4 units in the direction of 1 minus 1. Okay, so then find OB using OB equals OA plus AB. Yeah, easy enough. All right, what was the coordinates of B? Oh, that's what we're trying to find. Okay, and we've got the coordinates of A. OB equals OA plus AB. Well, then OA is going to be 3, 2 plus 2 root 2 minus 2 root 2. Okay, equals 3 plus 2 root 2, 2 minus 2 root 2. All right, hence deduce the coordinates of B. Okay, well then that's then the coordinates, isn't it? It's 3 plus 2 root 2 and 2 minus 2 root 2. Okay. All right. Yeah, skip that one. What do you think about this one? Question 8, triangle inequality. I'll come back to it if I need to. All right, moving on. Collinear points. So remember, the capital letters are points in space. So if you have a vector written in terms of two capital letters, we're going from, it's a vector that takes you from the point of A to the point of B. Okay, so the point of A to the point of B is equal to K BC. All right, and we call this a ratio division. So say point P lies on the line segment A to B, such that 3 points are collinear. So see they're all on the same line? That's what we're talking about. We said that P divides AB in the ratio of AP, PB. All right, so given that, okay, so we say ratio. All right, now a little trick to help you with this. All right, so if you consider it this way, given that, okay, let's find out. So A is equal to -3 on 2, and B is 5 on 1. 5 and 1. All right. First of all, I can work out A to B. That's one thing I need to do. Okay, so if we go from -3 to +5, then that is a displacement of 8. If we go from 2 to -1, that's a displacement of -3. Now, P divides AB in the ratio of 2 to 5. Now, what I like to do is I would then add the total is 7. So if you get 2 parts of 5 parts, if you mix them in together, like if you're making a recipe, if you have 2 cups of flour and 5 cups of milk, you have very milky flour, but you also have 7 cups in total. So think of it that way. That's where this division comes in. So the idea that, all right, so if you go from, the way to think of it, okay, so if you go from, and if you draw it, and these lines that you draw don't have to be consistent with the direction it's going. It's just a little guide to help you. So, okay, there's 2 parts and that. So that you can see that as a total of, say that's like 7 magic units, because there's probably not going to be like 7, but they will divide in this ratio. Yeah, so it's just about ratios, and then that will be 2, and then that's 5. So the way to think about it is like this. All right, so when maybe we have a position and we have another coordinate. There's O, there's A, there's P, and there's B. Okay, so think of this way. All right, so if the length from A to B was 7 something, then the length from A to P would be 2. So 2 to 7. So you can think of it this way. So if we want to find P, we want to find O to P. Now, the way to get from O to P is by going from O to A and then from A to P. But we don't know where P is. But what we do know is that it is along the line from A to B, and it has a ratio of the length. So it's going to be 2/7 of AB. See what we've done there? Okay. So O, actually no, let's just put them in. What's OA? Well, A is 3, 2, so the vector to take you there is -3, 2, plus 2/7 of AB, which we already worked out, 8 minus 3. All right. So let's bring those together. Sorry if you didn't see that. Okay. -3 plus 2/7 times 8 and 2 plus 2/7 of times -3. Boom, equals, all right, so we've got -3 plus 16 on 7 and 2 minus 6 on 7. Okay. And if you condense that down, I'm just going to look at that and just do the answer. So -5 on 7 and 8 on 7. There you go. Yep, that's how you do it. All right, so Okay, I think that with that example, we can give those a try. And given that, find R, divides that. All right. All right, so question 4 seems a little bit different, so maybe we'll give that one a try. But try it for yourself. Maybe just pause if you're brave. Give it a try for yourself. All right, so show that these are collinear. Well, how can we do that? So that's a little bit different. If we show they're collinear, then we're showing that they parallel and share a point. So if I went to P, if I said PQ, now if I just go in kind of, actually maybe I'll have a look at it. All right, see if we go from 1 to 3 to 7. You see that there's an increase in the x coordinate. Maybe I'll go in that order. So I won't go PQR. I'm going to go RPQ. So I'm going to go RQ. I think this will just be easier to spot if I do it this way. R to Q is, all right, well, if I go from R to Q, I've gone from 1 to 7, which is 6. I've gone from 9 on 2 to -3. Now, just so I've got it here, I've got my calculator set up as well in this new system. So if I go, you can write it down, but I'm just going to practice this. 9 divided by 2. No, what am I doing? All right, -3 minus 9 on 2 is -7 on 5 is how far you move across. That doesn't seem right. 7.5 would be, or that, yeah, that's 15 on 2, minus 15 on 2, if you prefer. So put you away. Yep, so that's how far you've moved R and Q. Then we'll go from Q to P. Q to P. So I really think Q is the middle point, just in terms of the x. Because if we go from Q to P, no, hang on, no, it's not. What have I done that for? Well, okay, never mind. All right, so actually R to Q is actually the larger one, and we're dividing out, and P's in the middle. So let's go R to P. It doesn't really matter. I mean, some of them can be backwards and anti-parallel. You can actually do it a whole bunch of ways. But R to P, you move 2, and okay, so we've got 9 on 2, which is 4.5. If you take 2.5, you've got that, so that's -5 on 2. Okay, so think about that. Yeah, it looks like basically this is 3 times that. So you can say that RP times 3 equals RQ. Now, so these are collinear. Why? Because they are parallel and they share a common point. So that's collinear. All right. Now the last part is find the ratio which divides the R to 2. The middle point, as I mistakenly pointed out, so that's P. Okay, so, well, in that respect, I can just go and find, okay, from R to P, R is the furthest, no, R is the least far in terms of that. So R to P, you've got that length. Yes. Okay, RP, I've actually already solved it by doing this. If I just divide that across, RQ. Okay. In terms of that. And thereby, okay, so the ratio there is, if you think of it this way, so you go from R, if you go from R to P, sorry, and then Q, there we go. It's 1 to 2 because they add up to 3. So thereby the ratio, I should say, Q divides Let me start that. Q divides. No, it doesn't. P divides. Get it right. P divides RQ in the ratio of 1 to 2. So R to P, that's the one part, and then there's the 2 there. So R to Q, so you got to 1, 2. Okay, that's how you do that. All right, now I think this might be all I really want to do. Yep, I'll save this one for another time. So good luck, have a go at those ones, and send me your questions as you need to. All right, take care.